Hello. Today I would like to proceed with assembly processes, and the next process to regard is electrically conductive adhesive bonding. That process is based on a paste that is very similar to the pastes which we use in thick film technology. This pasty material is polymer based, so the processing conditions will be quite different. There are mainly two applications. One application is die attachment, and the second application is surface mount technology. The process is also similar to reflow processes. First, we must produce a screen, and that screen is used to print that adhesive paste onto a substrate that can either be a printed wiring board or, for instance, a thick film substrate. After the printing of that paste, the device is placed. So we bring the device here, put it on, and in the next step we go into a hardening process. So typically that can be a batch oven, and here the epoxy or the polyimide is hardened. In a similar way, I would like to show you the process we have developed for die attachment. So here we have, for instance, a diode of 7.5 by 7.5 millimeters. These diodes are quite thin nowadays, only 70 micrometers. Or the IGBTs, which is transistors, are a little larger. And these should be placed onto substrates, and in our case it was direct copper bonded aluminum oxide, and you can see it here, this thick copper layer on the alumina. Here the electrically conductive adhesive is dispensed with a so-called needle dispenser. For instance, we can make a certain pattern which is like an X, and the chip is placed, and in that case, for instance, we have a curing condition of between 150 degrees centigrade and half an hour, or 180 degrees centigrade and only 15 minutes of hardening. Typically, the wet thicknesses of that adhesive before curing are typically 40 to 60 micrometers. Also, it is important to have certain patterns. These can be dots or lines or Y-bone, so some kind of wishbone pattern, or even a cross. The trick with this dispensing is that when we place the chip onto it, the material will flow. It will flow away from the middle, and when we do it properly, the area of the adhesive will be slightly larger than the area of the chip. That's the ideal process for deposition of adhesive and subsequent pick and place operation. So now let's come back to the surface mounted device. In that image here you can see a chip capacitor, probably it's type C1206 or such size. And here you can see again it's an aluminum oxide substrate. Here we have a silver palladium thick film. Here is the adhesive. It was printed in that case with a screen printer, and then the chip was placed. What is not so beautiful here is there is no gap between the chip capacitor and the substrate. So for reliability reasons, it's better to have a certain gap here. That material here is something like barium titanate, and the metallization here is also silver palladium metallization. So that is a typical technology we developed for high temperature automotive circuits. So now let's first have a look at the adhesives. And there are many possibilities. One of the possibility is the resin of which it consists, and these resins can be either epoxies or polyimide. The filler of such polymers must be there in order to achieve certain properties. In the case of electrically conductive adhesives, we have a silver filler of up to 80 or even more than 80 weight% of silver. We can also have a filler of aluminum oxide powder. Here the weight percentage is significantly lower, and these are more for thermal conduction, while the silver is both used for electrical and for thermal conduction. On the other hand, we can also use polyimide as a resin, and here are several examples. What is important, if you buy such adhesives, you must store them under special conditions. For instance, the so-called frozen epoxies, they are stored and transported under dry ice. And for instance, you can keep them for 1 year at -40°C. So that's very frequent. You just have them frozen in a way. The chemical reaction of the epoxy with the hardener is frozen. All of these epoxies nowadays are pre-mixed, so you don't mix two constituents, but they are pre-mixed because then the properties are more uniform than when you mix it yourself. And that frozen slows down the chemical reaction between hardener and resin, and so you can keep it for long. These SnapCure adhesives have something special. Here the hardener is trapped in some microcapsules, and when you go beyond a certain temperature, for instance, you go beyond 200°C, these capsules release the hardening agent, and then you have an immediate hardening. So the disadvantage of such electrically conductive epoxies is that normally you do not know much about the chemistry in it. You know it's an epoxy, but you do not have much more information. Material which is also important is polyimide, and the advantage of polyimide is that it has a significantly higher operating temperature. So you could go up to 350 for longer times with polyimide, but you can only go to 150 to 175°C for long operating times with epoxies. Typically, the silver material here that has a thermal conductivity which is 2 watt per meter Kelvin. That's a factor of 10 worse compared to, or a factor of 20 even compared to solder alloys. The adhesives which are filled with alumina have an even lower thermal conductivity. What is given here is some shear strength, 10 Newton per square millimeter or megapascal. That is something which is not too high, but it is sufficient for almost all applications. So these silver-filled have a relatively low electrical resistance. It's higher than for solder alloy, but it's sufficient in all cases. What is also important is while you use so-called no clean fluxes in soldering, here you must limit the content of chlorine especially in these alloys, because chlorine in combination with silver can lead to severe corrosion problems. So here the chlorine content should be limited. For these adhesives, the glass transition temperature is relatively low. It can be between 80 and 120 or sometimes 150 degrees centigrade. Okay. Now, when you look at such conductive adhesive bonds, you are interested in reliability. For instance, in automotive applications, reliability tested with 3,000 temperature cycles from -40 to 150 degrees centigrade. And now, when you take here the shear strength and you just relate it to the starting value, you can say, depending on the device that you examine, you can see that either the shear strength will be maintained constant, or in some cases it will decrease down to, let's say, 60%. Here on the x-axis is the number of cycles n. What is also interesting is that this maximum increase is not for the biggest and not for the smallest devices, but for some intermediate size. So here that's a 1206 we have here. But generally it means that up to 3,000 cycles we still retain a large shear strength, and that means we can build very reliable circuits which also can withstand high operating temperatures. Still, to give you some data about the shear force depending on that size, so 10 Newton is roughly 1 kilo, and here 200 Newton is roughly 200 kilo. So these assemblies are quite strong. On the other hand, also the resistance is very limited, maybe in the 20 to 40 microohms region, but it is not zero. When we look at these polymers, it is always important to look at thermal mechanical properties. So we look at CTE and Young's modulus, and both are depending on temperature. First, we test for CTE. So we just look for the length change of a certain sample. here that length change is given in micrometers, so it's related to the initial length. And so we can see there is a progressive behavior, and if we want to simplify it, we can say we have a low temperature linear range and a high temperature linear range. And here we can say T is above Tg, and here is T below Tg. When we take the first derivative of that curve, then we can say the CTE, CTE alpha is dL divided by L0 derived by temperature. That is the definition of CTE, and so we can see we have a low temperature CTE and a high temperature CTE. And depending on the material we have, the glass transition can be between 20 and 150 degree centigrade, and the transition from low temperature to high temperature behavior is a factor of, as we see, between 2 and so we have 2 times to 4 times increase of CTE with temperature. At the same time, we can regard the Young's modulus. That is the Young's modulus derived from a higher frequency bending test. And here we can see that the Young's modulus will go down. In that case, also it already went down around 60 degree centigrade. At the same time, that modulus here gives the damping properties. So that material becomes softer and more viscoelastic than elastic. Again, here we can see for these different materials, typical adhesives have Young's modulus, which is somewhere between 5,000 and 7,000 at low temperatures. It decreases somewhat with temperature until we arrive at the glass transition. And here again, there is a steep decrease. And here you could say the Young's modulus is roughly divided by 10 when we go beyond the glass transition temperature. So if you regard these curves, you see that we will be able to select a certain material with respect to CTE and Young's modulus. Of course, the materials with very low elastic modulus, they are used for low stress, for instance. And these here are, for instance, for high temperature applications. So we want to have stability in circuits which operate at higher temperature. When we look at the shear strengths for the other materials, I told you 10 megapascal of shear strength. In our case, we did an investigation of our own. Here we had something like 28 megapascal, and when it's colder, it's stronger. and going down again, it goes maybe from 30 megapascal to 3 megapascal. So again, the strength is decreased by a factor of 5 to 10 when we come from a low temperature range to a high temperature range. Anyway, most circuits also operate in that high temperature region, and the strength of these die attachments is still sufficient. Okay, so we have here two processes up to now. One is soldering, the other is conductive adhesive bonding. Both processes can be used for die attachment and for surface mounted devices. What you could do is compare these tables. I will not go into the details here. For applications where we want to have a high conductivity, conductive adhesive bonding is often not sufficient because 2 to 5 watt per meter Kelvin is not enough. On the other hand, modern semiconductors also go to temperatures approaching 200 degrees centigrade or going above. Both applications are no longer possible with solders. Also, when you use solders, you would have to use lead solders, and lead solders are no longer desired in electronic fabrication. They are not definitely forbidden for that application, but everybody tends to get rid of these materials. And so a new process has been developed which is called silver sintering. Silver sintering means we have a sinter powder or a sinter paste, and similar to thick film technology, that will sinter, but it will sinter at low temperatures. Typically, it will be able to sinter because we have very fine particles between 0.3 and 8 micrometers and special sintering additives. And in that way, we can mount chips which have backside metals like titanium gold or titanium nickel gold or titanium silver onto DBC substrates, and these substrates are also typically copper with metallization of nickel gold. So sintering works only against noble bonding surfaces. Everything else, bonding against copper, is more in a research state. So maybe we first have a look at such sintering equipment. That is something in our lab. Here you can see 2 plates. These plates are heated, and in between you put the substrate, and on the substrate here are the individual chips. The deposition of the paste and the pick and place is very much the same like in adhesive bonding. So you can screen print it or put it on with a needle dispenser like in adhesive bonding. Then you place the chip, and all of this is shifted into that sinter press here. Here you can see the individual parts. For instance, that upper hot plate and lower hot plate must be well controlled with respect to temperature. And in that way, we do not just produce one single die attachment, but we can perform many die attachments at one time. Going back to the properties, for instance, one paste operates above 220 to 240 degrees centigrade. Time is between 5 and 10 minutes. That paste has a low pressure of 6 megapascal. it is a so-called no pressure paste. On the other hand, that is a so-called high pressure paste. And here again we have a similar temperature range, similar short times, but the pressure here can go up to 60 megapascal. Unfortunately, not all substrates will survive such a high pressure. On the other hand, here you can get very high strength of the die attachment after the bonding. That paste here is also a no pressure paste, and here you really do not need any pressure. That is a typical profile, so you have a limited range of heating. You keep it at a low temperature in order to get rid of some organic substances and volatile substances. Then you heat quite fast, and after that you apply the pressure and the highest temperature for a quite short time, and after that you can cool it down, for instance, with controlled water cooling. So that's a typical process we have used with our sinter press, which you can see here. Now the result, for instance, to show you what the difference is with respect to pressure or also with respect to time. And so you can see here, you can even see the individual powder particles and the porosity in between. So that is sintered only partly. And if you put on more pressure, you give more bonding energy to the process, and that means you have a very dense connection. And here that is just pure silver, and that silver is very stable. Also, silver is the material with the best thermal conductivity you can have from the metals, and in that way you can have an ideal connection for IGBT chips. What you can also see here, the substrate, our substrate here is some printed wiring board. It is not FR4, but it's a so-called help material. Okay, so we can see using that process we can produce very strong interconnections, especially for power electronics. Presently, my staff is working on processes to use such connections for sensor die attachment. Okay, but there are more processes which we can use, and one of the relatively old processes is eutectic bonding. So do not mix it up with eutectic soldering. Eutectic bonding, also called alloying, is based on the binary phase diagram of gold and silicon. When you put both materials together, you can mix it, and you just have one phase. If you would make a liquid of such phase, for instance, throwing together 30 atomic percent of silicon and 70 atomic percent of gold, in that way you could have a liquid which consolidates at 370 degrees centigrade in a eutectic reaction. So that reaction is melt gives gold plus silicon, and both in a very fine, grainy eutectic structure. On the other hand, you can also use that effect if you just bring gold and silicon into contact and heat it above 370 degrees centigrade. It will melt locally, and when you cool it, again you have a eutectic. So the trick is, while gold has a melting temperature of 1063 and silicon has 1404, the melting point of that eutectic is just 370 degrees centigrade. Unfortunately, silicon has an oxide layer, so typically we have silicon oxide, and that would prevent wetting with gold, and so the silicon oxide would keep the gold and the silicon apart, and so there could be no eutectic reaction because there is just a layer in between. For that reason, the silicon chip is typically coated with a chromium layer and a gold layer, and the silicon oxide must have been etched away before the chromium is put on. And also we can use optional a preform, which is something like a solder consisting mainly of gold and a little silicon, and we can put that in between. We pick and place that, we put on pressure, and we scrub, so that means we have a rubbing movement which rubs away the rest of the silicon oxide which could be there, and in that way we can create a eutectic structure by that process at 430 degrees centigrade. Of course, this has to be performed under nitrogen atmosphere because we must avoid oxidation of silicon, and that works out quite fine. It only has one disadvantage: that eutectic structure is quite brittle and hard. So it cannot give relief against thermal mechanical stress, and that means that is a process which is extremely stable, but it can also be a high stress process. So if the substrate and the chip are not thermomechanically adapted, you can only go for small chips. If you want to have larger chips, you take something which is compatible with silicon, so it could be Alloy 242 or Covar, or you use something like aluminum nitride, which is very close to the silicon in CTE. Still, there are more possibilities, especially when you want to produce sensors. For instance, at some time we investigated this MEMS chip. That is an acceleration sensor. And for that chip, we made a cross section, and what we were wondering is that material under the chip, it looked very much like an adhesive. And also what we were wondering about is that layer under the chip was very thick, and then we analyzed it in more detail, and then we found out that the binding phase, it is some glass, and the filler we have here, that is just silver. So we have so-called glass solder, or some also say glass adhesive. Of course, you can imagine the melting point of a glass is quite high. So a glass is not like epoxy that reacts at a low temperature and gives a bond that is stable to a higher temperature, but a glass is a reversible, you could say, thermoplastic material. So you heat it, it becomes liquid, you cool it, it consolidates again. Typical such glass contains 80% of silver. The rest is some glass. The main constituent here in that case is, for instance, vanadium oxide. That is an oxide which melts at a quite low temperature. So the whole material is processed between 340 and 400 degrees centigrade. Again, that is an attachment for a good CTE match. Again, we know a glass, it's relatively brittle, and the glass is relatively hard. So that's such a typical process. Again, like in all cases where we have a paste that is first deposited, that paste must be pasty, so we can deposit it. Then the paste is dried, all of the organic parts are evaporating, and then around 300 degrees centigrade the glass will melt. We keep it for a sufficient time so the glass can wet the surfaces, and then we can go down again with temperature. And in that way we can also produce high temperature bonds. For instance, we have done such things for high temperature pressure sensors. What is also important is against which surfaces can we do our three processes. One would be soldering, second would be conductive adhesive bonding or silver sintering, and the third would be eutectic bonding or alloying. So we can solder against nickel, silver and copper. We can also bond with soldering against the undermetallization plus a thin gold layer. In thick film substrates we can we can solder against silver palladium, which is most important metallization. We can solder against silver. On a printed wiring board we can do the soldering on tin lead, on nickel gold of course, and on copper. The adhesive bonding, if it should be conductive, we can only do it against noble metals like gold, silver, also palladium. Ceramic packages, most cases have a gold surface. thick film substrates also have either gold or silver palladium, for instance. And so if you want to sinter or electrically conductive adhesive bond, then you always need a noble surface. For the eutectic bonding alloying, you typically need always the combination of silicon plus gold, and here the gold also must be a thicker gold because it becomes part of the alloy which you form here. Again, when we look at the individual advantages, for instance, silver sintering has long lifetimes, high strength, and what is most important, lowest thermal resistance. Eutectic bonding has a good ohmic contact, high strength, but it leads to high stress, and not all chips like it. Soldering has a good ohmic contact, has a low thermal resistance, high strength. Also, it's cheap, but you cannot get the ultimate properties like you can get them in silver sintering. So often for very high performance application, silver sintering is preferred. Adhesive bonding, that's a process which is quite cheap. Also, the adhesives themselves are quite expensive, but automation is very simple. The process itself is simple. You can play around with hardening temperatures. So for the same adhesive, you can use quite low temperatures of 100 degrees or go up to 200 degrees, and in that way you can also control the stresses you have. On the other hand, thermal stability is limited. Polyimides, they are quite difficult to work with, and they have a better thermal stability compared to epoxies. And also we have this silver glass, which has a good thermal stability, and when the CTE fits well with a silicon chip, we can also have very stable connections, especially for sensors. Okay.